So my name's Rob, and this is a course on introductory statistics for the psychological sciences. And today, we're going to be doing a conceptual introduction on factorial ANOVA. In doing so, we're going to kind of build on the prior understanding we developed in prior lectures on one-way analysis of variance, or one-way ANOVA. And so today, we're just going to be adding some new concepts into that foundational knowledge that we've gained. In the second part of this lecture, we're going to go through how to compute a factorial ANOVA and the formulas involved, how to do the ANOVA summary table. And then in the next lecture, we're going to do a full, from beginning to end, one-way or two-way factorial ANOVA example, including all the calculations and the APA style write-up. Okay, so if you find this video helpful, don't forget to like it and subscribe, and hit the notification bell so you can get updates on future videos just like this one. And as always, I'm going to chill right here and lecture a little bit. And over here are the PowerPoint slides. And typically we have a whiteboard up here, but today, since it's just a conceptual introduction, I've done away with that. So, well, why don't we begin on an introduction to factorial ANOVA. Okay, so I want to bring up again this distinction that we addressed a couple lectures ago, the distinction between factors or independent variables and levels, right? So this is an important distinction. So we might have a factor called treatment type, and within that we have three levels: cognitive behavioral therapy, mindfulness, and control condition. So this is absolutely essential, especially as we get into factorial ANOVA, that you're able to distinguish between factors versus the levels of a factor. So again, we could have a factor biological sex, and that might be male, female, and such. So this is a very important concept, so be sure whenever you are reading a problem or something that you understand this distinction between independent variables or factors and the levels that come underneath them. So for example, here we have a one-way between subjects ANOVA design. It's one way because there's one factor, right? And it's between subjects because each level of the factor contains unique people. Some people get CBT, some people get mindfulness, some people get control. Now, in a one-way ANOVA, what we're doing is we're evaluating the differences for two or more groups. And the distinction between a one-way analysis of variance and a factorial analysis of variance is the one-way is limited to only assessing one factor or one independent variable. Factorial ANOVA is whenever we have two or more factors. And these can be either experimentally manipulated variables, or they could be cross-sectional in the sense that you're just comparing naturally occurring distinctions in a population. But and then again, each factor can have two or more levels. So let's look at how this would turn out. So here, a factorial ANOVA, we have two factors here. We've got treatment type, right? CBT, mindfulness, and control. And then we have veteran status, whether they're a veteran or not a veteran, right? And so here, we call this a 2x3 factorial design. So keep in mind the number of numbers that we have in that beginning of titling this test, 2x3. The number of numbers is how many independent variables there are. And the value of those numbers represents how many levels that independent variable contains. So here we have a 2-level factor, veteran, non-veteran, and a 3-level factor, CBT, mindfulness, and control. Thus, this is a 2x3 factorial design. And one thing you can see here is that 2 times 3 is 6. And we have precisely 6 cells in this chart that we've got. And so that's kind of the logic behind why we have the, well, it's a 2x3. So if we added a level, right? So say we added the level mindfulness-based cognitive therapy, MBCT, to the treatment factor. Well, now this is a different design, right? This is a 2, veteran status, by 4, treatment status, right? Okay, so factorial ANOVA is one in which the effects of 2 or more factors, in other words, independent variables, are either assessed or manipulated in one experiment. Now, the two-way ANOVA allows us, in one experiment, to evaluate the effect of the 2 independent variables and the interaction between them. And this is the key benefit of a factorial ANOVA, right? You could, if you had 2 independent variables or 2 factors, you could do a one-way ANOVA on the first independent variable, and then a one-way ANOVA on the second independent variable. But then we get into the issue of alpha inflation again, and in addition, we lose out on a certain piece of information called the interaction, and this is key. So the two-way ANOVA allows you to not just test the effect of the first factor and the effect of the second factor, but how those 2 factors interact with each other. In other words, how does the effect of one factor on the DV depend on the other factor? So this would be an example of a design that has 3 factors. Now we have veterans and non-veterans. We've got CBT, mindfulness-based cognitive therapy, and control. And then we split it again across males and females. So we've got factor 1, treatment type, factor 2, veteran status, factor 3, biological sex. So this you could write out as a 2 or a 4 by 2 by 2 between subjects factorial ANOVA. And if you do the math, 4 times 2 times 2 is 16, and there is precisely 16 cells that we have in this design. That means that because these are all between subjects factors, there's going to be 16 different total groups of people. And using a factorial ANOVA design, we can look at how these different factors interact with each other in their effect on the dependent variable. Okay, so when we do, we're just going to go through, to keep it simple, we're going to go through some of the concepts that underlie two-way ANOVA. Now, naturally, these are going to expand to, a 3-way ANOVA or a 4-way ANOVA. But we'll start with a simple example. So a 2-way ANOVA is essentially asking 3 questions. We're asking, is there a main effect of factor A? Is there a main effect of factor B? And does the effect of one factor on the dependent variable depend on the other factor? And this is called the interaction effect. Right? And so again, this third question is a key, the key advantage of doing a factorial design, because it allows you to examine not just these main effect questions that you would get by doing 2 separate ANOVAs, but also the interaction term, which you cannot get by doing 2 independent ANOVAs. So let's go through an example here. Caffeine and Cognition. So suppose we have this design where the dependent variable is going to be problem-solving performance. So essentially, people take a test under different conditions, right? Some people take a task that have a test that is a very simple problem-solving test, and some people have a task that's a very complex problem-solving test. So factor A is going to be task complexity. And then the other independent variable that was manipulated by the experimenter is how much caffeine a person receives. In one condition, some people receive no caffeine. In a second condition, people receive 100 milligrams of caffeine. And in a third condition, they receive 200 milligrams of caffeine. So here we can see, on the basis of these factors and how many levels each factor has, we have a 2 by 3 between subjects factorial ANOVA. So we go in here, and again, we're asking 3 questions. The first question is there a main effect of factor A? And this question is essentially just doing a one-way ANOVA on factor A, which was task complexity, right? So it's just looking to see, does task complexity influence problem-solving performance? Importantly, probably a better way to say this is, does task complexity influence problem-solving performance without taking caffeine dosage into account, right? So we're not interested in, when we're looking at the main effect of factor A, we're not interested at all in the influence of factor B. So to figure out if there's a main effect of task complexity, what we want to examine is the difference in the marginal means. So essentially, we want to collapse across the caffeine dosages, right? We just want to average all the values for simple tasks and all the values for complex tasks, and we put them here at the bottom in that marginal mean area, right? And that's simply the average of their dependent variable, their problem-solving performance, averaged across each level of caffeine dose. And so essentially here we're comparing simple task to complex task. And when we look at this, we can say, okay, is 26 different from 88? Seems pretty different. Now to formally test this, we're going to need to compute an F test, and compare it to a critical value and all of that, which we will go into in the very next lecture. But here I'm just trying to conceptually go over what main effects interactions are without going into the nitty-gritty of the computation. So just eyeballing this, we can say, oh, it looks like simple tasks scored lower than complex tasks. And we can plot that out in a graph, and clearly we see this angled line, simple tasks lower than complex tasks. So the next question is there a main effect of factor B? What this is asking is, does caffeine dosage influence problem-solving performance? So we're going to do exactly the same thing as we did for factor A whenever we're doing the main effect of factor B. Now what we want to do is disregard task complexity. We want to collapse across task complexity. So we're going to average 32 and 80 together. And then we're going to average 25 and 91 together. And then we're going to average 21 and 95 together. And we're going to get these marginal means on the right, shaded in green. And we look at those, we say, well, are those different from each other? Well, I mean, whether or not the difference between 56 and 58 is a significant difference is going to depend on your statistical power. So it's very important to understand that you would actually need to do an F test and compare your F obtained value to an F critical value to really determine if this was a statistically significant difference. But here we can look at this and we're just eyeballing it and saying, you know what? They look pretty much the same. The difference between 58 and 56 is nowhere in the ballpark as the difference between 26 and 88, right? So, okay, so we would say there's not really a difference in caffeine level here. And so we can graph this out. We can see they don't look very different whenever we plot them out. We're not getting an angled line. Okay, so now the third question, and this is the interesting one, is there an interaction? Does the effect of one factor on the DV depend on the other factor? So what this is asking in the context of this problem is, does the effect of caffeine dosage on problem-solving performance depend on the complexity of the task? I mean, it could be that caffeine might be helpful for very simple tasks, but caffeine could impair performance on complex tasks. And therefore, maybe that's the reason why caffeine dosage, we didn't get a main effect of caffeine dosage, but maybe there's an interaction effect. Maybe it looks like how caffeine influences problem-solving performance depends on how complex the task is. So, to examine this, we're not using the marginal means anymore. What we're doing is we're looking at the differences across one factor and seeing if those differences are significant, right? So we might take 32 minus 80, 25 minus 91, 21 minus 95, and see if the magnitude of those differences is different. And that is essentially an interaction effect. So here we can see, when we plot this out, we can see these lines aren't parallel. It looks like there may be an interaction effect here. So this is just the general overview of how conceptually what is an interaction, what are main effects. So let's go in to another example. And in this example, what we'll do is we'll try to build up our skill at being able to look at some basic line graphs and determine, but just by eyeball, if there's likely a main effect or an interaction effect going on. So suppose you want to know whether exercise helps increase sleep, depending on the intensity and time of day when the exercise occurred. So we have a 2x2 design here. We have our dependent variable, which is the amount of sleep in hours. And we have independent variables. Factor A is exercise intensity, which is going to be light versus heavy. And factor B is going to be the time of day of that exercise, morning versus evening. So we've got two factors, each with two levels. And so this is going to be a 2x2 factorial design. So for each figure, I'm going to show a bunch of different figures that could represent the results. And just by examining these, try to see if you can determine if there's a main effect for exercise intensity, if there's a main effect for time of day, and if there's an interaction effect. So here we go. So main effect for exercise intensity. It doesn't look like light is higher than heavy. So essentially what we're doing when we're looking at this main effect here is we're averaging the data points of the red and the gray line for light and comparing them to the average of the red and the gray line for heavy. And they don't seem that different. So this is not going to be a main effect of exercise intensity. Okay, and then morning versus evening. Well, the red line isn't much higher than the gray line or lower than the gray line. They're right on top of each other, right? So if we imagined trying to find the average of light and heavy on the red line and the average of light and heavy on the gray line, so we had 2 points in the middle, right? This is going to be our main effect of time of day. So now the interaction effect is whenever the lines are not parallel. Well, certainly these lines aren't parallel, but they're not really an X either. They're pretty right on top of each other. So this is really an example of nothing's going on. There's no main effect for either of the factors, and there's not an interaction effect. So here, we can see that there's a main effect for exercise intensity, right? Light, the average of the gray and the red lines for light is lower than for heavy. Now there's no main effect for time of day because the gray and the red lines are right on top of each other. And there's no interaction effect because these lines aren't really crossing. I mean, they are slightly, but they're really just right on top of each other. And so here is an example of a main effect of factor A. Now this would be an example of a main effect for time of day, right? So we can see that the average for morning is higher than the average for evening. However, these lines are parallel, so there's no interaction. And it appears that if we average together the red line and the gray line for light, and the red line and the gray line for heavy, they would be about equal, right? They would average in between those two lines. And light and heavy would be about equal, so there's no main effect of exercise intensity. Okay, so here we've got a main effect of exercise intensity and a main effect of time of day. But there's no interaction effect. These lines aren't crossing each other. And then here is an example of what's called a crossover interaction, where if we can see there's an interaction because they're clearly crossing over each other. However, there's no main effect for exercise intensity and no main effect for time of day. So think about this, right? If we average the value at light for the red and the gray together, we get a point in between those two lines, it's not going to be different from the average of the point for heavy in red and gray. Those 2 points are going to be approximately equivalent. Okay, so that means that there's no effect of exercise intensity. At the same time, if we average across light and heavy, and we look at the average point for the red line versus the average point for the gray line, right? So again, this would be looking at the value of evening light plus evening heavy divided by 2, right? Morning light plus morning heavy divided by 2. We would get that point right in the middle where it's x'd out, right? So both of those are not going to be different from each other. So we can see that there are no main effects here, but there is a significant interaction. Now here is an example of whenever we have a main effect, another main effect, and an interaction effect, right? So we know these lines, while they might not be crossing in this figure, if we draw those lines out to infinity, they will cross. So this is an interaction. Now, we can see the main effect because for exercise intensity, because the average of the red and the gray for light is going to be lower than the average for the red and gray for heavy. We also have a main effect of time of day, right? So if we average across light and heavy for the red line, that's going to be lower than the average of light versus heavy for the gray line. Okay, so this, the whole key here is to go through and try to visually just inspect the data. You want to interrogate it with your eyes and figure out if there are main effects or interaction effects by visual inspection. You also want to be able, need to understand how a main effect is computed. What is it comparing? And we did that with marginal means. So in the next lecture, what we're going to do is go over the different steps used to conduct a factorial ANOVA. And we're going to do things like have a new ANOVA summary table. But I hope this was a very helpful introduction to why we do a factorial ANOVA, the extra information it provides in the form of exploring interaction effects, and the conceptual distinctions between main effects and interaction effects, and how to visualize them. Okay, so if you found this helpful, don't forget to hit the thumbs up button, and yeah, I will see you at the next lecture. Have a great day.